So the last lecture was some sort of introductory to the course. I try to demonstrate the basic ideas that we would like to implement during this semester, and in particular it was important to show the idea of asymptotic relationships, like f is asymptotic to g as x goes to something, x naught, and x is much larger or much smaller, negligible with respect to g in such limits. Today we will start implementing these ideas to the most important field of branch of mathematics for physicists, which is the solution of differential equations. So every physical problem, by and large, with probability 1, when you start with a physical problem, you end up with a differential equation. And we want to provide a systematic approach to the solutions of these differential equations. Before starting, I would say that we have to, somehow one would like to rethink the idea of what we call the solvable differential equation. Because if this is a differential equation, right, plus x equals 0, can you tell me what are the solutions of this differential equation?
It's the sum of e to the plus minus ix.
Okay.
It.
Otherwise, you can say it's a sine and cosine, right? Cosine t or sine t are solutions. So the most general solution is x equals to a cosine t plus b sine t. But if you think about it a little bit differently, in what sense the cosine and sine means a solution? If the solution is Bessel function, it's also a solution, right? And if it's some function that we don't know, okay, so let's define the solution for this specific equation as, who knows, your named function, and that's it. So what does it mean that the equation is solvable? So maybe it's better to think about equations as solvable if we can calculate all the coefficients of a given power series, which is the solution of the equation. This is not an exact concept, but I would like to try to explain it. So sine and cosine are functions that we know how to write them in a power series to infinite order, right? So we know what are the coefficients. If we can calculate the coefficients, then we can say that we have solved, so to speak, in the sense that I will try to explain later, the differential equation. So, for example, let's start from an equation that is, first of all, nice to as a demonstration, but also this very same equation will turn out to be very important in the asymptotic analysis that we are going to do during this semester. And this is the equation y double prime equals xy. So y is a function of x, and the second derivative of y with respect to x is equal to x times y. Any of you know what this equation is? What's the name of this equation?
Airy function.
Very good. Very good. This is Airy equation. This differential equation is known as Airy equation. Okay? Now, so how to solve such an equation? It's not simple. There is no, you cannot write sine or cosine. the solutions, how many solutions such an equation have? Two, because it's a second order differential equation. And the solutions for these equations are known as Airy function and Bailey function. Okay? So these are the solutions. And now let's try to write them down as a power series. As I said, I will say that I've solved something if I can write a power series that and calculate all the coefficients. Okay? So let's try to do that. What are we going to do? We are going to write y as sum from n equals 0 to infinity of a n x to the power of n, which means that y prime is a sum from n equals 0 to infinity of n a n x to the power of n minus 1, which means that y double prime is a sum from n equals 0 to infinity of n times n minus 1 times x to the n minus 2. Any complaints about that?
Shouldn't we do for y prime from n equals 1 and for y prime prime from n equals 2? Because if we don't, we get 1 over x.
Again?
For y prime,
He wants the index to start.
shouldn't the index start from 1?
No, this is completely, if you assume that, then this is a logical consequence. And this is the logical.
No, but
clearly,
Yeah, it
this
doesn't matter.
and the n equals 0 term will not contribute because n equals 0
Oh,
gives
yeah.
you 0, and then n equals 0 and n equals 1 term will not
Oh,
contribute here. I agree. Okay, now, you can manipulate these power series, but I am not good enough in that. I must write to myself, first of all, the first few terms in order to get the idea of what is going on, and only then I am able to manipulate the power series directly. So let's go back to this equation, to the area equation, and try to see what is written here. So y double prime, as we say, the n equals 0 term will not contribute because of that. The n equals 1 term will not contribute because of that, right? So it starts from n equals 2. So the y double prime will give me what? 2 times x to the power of 0. So it's 2, oh, I've forgotten, this is a n, right? I forgot. So 2a 2 plus, what's the next term?
What are you
3.
3. 3 times 2 is 6. So 6a3 times x. You see, I'm just writing the first few terms in this expression.
Why?
What?
Why?
Just to train myself.
Huh.
Right? And what is the next term?
12, say 4, x squared.
N equals 4. So 4 times 3, so it's 12. A 4 x squared. Right? Plus, what's the next term?
20,
Yes, 20
a5.
a5 x cubed. Blah, 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 and this series continues for good. Okay? Equals to, so this is y double prime. Equals to what? X times y. What is x times y?
A0x.
Right? We can write it here. X times y is the sum from n equals 0 to infinity of a n x to the power of n plus 1. Okay? So what I'm going to get?
a0x,
a0x plus
a1x squared.
a1x squared plus a2x cubed plus blah blah blah. Okay? Good. So, what? So, okay. And now, because this is Taylor series, things to the left and to the right of the equation should be equal term by term in powers of x, because Taylor series are unique. Okay. So, what is So what I can deduce from this?
A2 is 0.
First of all, A2 must be 0 because there is no other term here to cancel it. What about A3? A3. What is A3?
A0 over 6.
A3 is A0 over 6. What about A4?
A1 over 12.
Is A1 over 12. What about A5?
0.
Also 0 because A2 is 0, so A5 is 0. You see? Okay. So this is just to get an idea of how this folds, the calculation of the coefficient. Now let's try to do that in a more abstract manner. Right? So we want this to be equal to that. Okay? And now what I will do, I will change indices. Okay? So what I would like to do is to have both the right side and the left side in power of x to the power of n. Okay? So this implies that I will define here, for this side, I will define m as n minus 2. Right? And I will get the sum over m. Now, I know that the first two terms are not going to give me any contribution here. Right? So I can start m from 0 to infinity. Right? And I will write here a to the m plus 2, m plus 2 times m plus 1 times x to the m. Now, for this side, I will define m as n plus 1. Right? And now this will be equal to the sum. But if m is n plus 1, then n equals 0. So for m, I will start from m equals 1. Right? So I will have sum from m equals 1 to infinity of a what? Of a m minus 1 x to the m. Okay? So I can immediately see that for the m equal, if I'm taking the m equals 0 term, I have a2, but there is nothing to balance it there, because a minus 1 is 0. A minus 1 is 0. Right? All the a's that are below 0, there is no a minus m is by definition 0.
And yeah, we can also see that from the equation.
Yes, I mean, this is a2 equals 0.
Has to be 0 at
Okay.
0 because it's x.
So,
times.
actually what we can say, what we can deduce from here is that m plus 2 times m plus 1 times a m plus 2 is equals to a of m minus 1. Or maybe better way to write that is to write m plus 3 times m plus 2 times a m plus 3 equals to a n. This is just changing the name of the index. Now, what does that mean? That this is the recursion relation, because it tells us that am plus 3 is equal to am divided by m plus 3 times m plus 2. Okay? Now we want to check ourselves with respect to the things that we already calculated, right? So for example, if I'm asking what is A2, I will find out that A2 has something to do with A minus 1, and as I said, all the minus terms are 0, so A2 is 0, and because of the recursion relation, it implies that the 2 is 0, the 5th is 0, the 8th is 0, and so on and so forth. So every A2 plus 3n is 0. Okay? Now, what about A3? Now, A3 will be A0 divided by, no, I did a mistake. Where is my mistake here?
You planet 3 on the, sorry, A3 is A0 plus 3.
Again?
You planet 3 instead of
sorry.
0.
A3, I should put m
equals 0.
m equals 0 here. Sorry, if I put in m equals 0 here, then A3, yes, okay, so this is fine, is A0 divided by 3 times 2, so divided by 6. See? Now what is A4? A1 divided by 4 times 3, so divided by 12, and so on and so forth. So this is what. You see? And we see that there are actually 3 chains. One of them is 2, 5, 8, and so on. And for all these, we have zeros. And now there are 2 other chains, one that start with A0, and all the 3 and so on, and one that starts at A1, right? And these are 2 independent solutions that correspond to the, okay, I will return to it in a minute. Well, fine. So my next goal is to write explicitly, I mean, for the moment I have the recursion relation, which is how the 5 depend on 2, or how 8 depend on 5, and so on. And I have, but what I really want is an explicit formula for am, right? So now I'm speaking about the chain 0, 3, 6, 9, and so on. So A3m. And I would like to develop a formula for A3m. You see? So what I already know is that m equals 0, A3 times 0 is A0. This is an arbitrary parameter, right? And A3 times 1 is A0 over 6. And then the question is, what will be the next, and so on. Good. So, can one tell me here what is actually A3m? According to what is written there, right? I can write the, okay, let's ask what is A3 times 2. So what is A6?
A0 divided by 6m.
Again, A3 divided by, now m is 2. So I should write here 5 times 4. Right? So I have 5 times 4. And this, but what is A3? A3 is A0 divided by 6 is 3 times 2, right? So this is A0 divided by 5 times 4. No. You cheated on me. Why?
It's 6 times 5, no?
Yeah, it's 6 times 5. Yes? Because here, okay, I use the m here and the m there are not the same thing. Sorry. This is m plus 3. So a3m is a3m minus 1 divided by, I mean, this is a different representation of the recursion relation. Okay? A3m is a3m minus 1 divided by what? Divided by 3m times 3m minus 1.
Why did you change the recursion relation?
No, it's the same recursion relation.
Yeah, but why did you switch the index?
Because this is more convenient.
Oh.
Right? So now you can say that a 2 times 3, so m is 2, is a3 divided by 6 times 5, right? Which is 6 times 5, which is a0 divided by 6 times 5 times 3 times 2. Okay? And can you now tell me what is a, this was 6, so what will be a9? 3 times 3. a9. What will be a9?
A0 divided by 9 times 8 times 6.
Oh,
times
okay.
8.
So you see the whole structure, right? This will be a6 divided by 9 times 8, so you have to add it to this. Right? So in general, a3m is a0 divided by 3m times 3m minus 1 times 3m minus 3m minus 2 is missing, right? 3m minus 3 times 3m minus 4 and so on and so forth. Or if you want it like a0 divided by 2 times 3, the first one, times 5 times 6 times 8 times 9 up to 3m minus 1 times 3m. Here I wrote it backward, here I wrote it forward. Good. What the hell is that? No, this is not factorial because the 4 is missing. If we have the 4 and the 7 and the 10, then right, it was factorial.
It's a factorial divided by the second, like the factorial where you have like the more than one exclamation mark.
No. Okay, of course, you can define this as a factorial with 75 exclamation marks, right? But there is a better way to write it. Okay? First of all, let's divide all these numbers by 3. So I'm going to write it as a0 divided by, how many terms do we have here? We have 2m terms, right? Because every other m add 2 numbers. So I will divide it by 3 to the power of 2m. By the way, this is 9 to the power of m, of course. Okay? And now I will divide every number in this chain by 3. I just take the 3 outside. Okay? So what I will have 2/3 times 1 times 5/3 times 2 times 8/3 times 3 times 3m minus 1/3 times m.
Now you got factorial.
Again?
Now you got factorial.
Oh, now I have 1 times 2 times 3 up to m. So I can describe some times, right? I can describe half of this product as m factorial, right? So what remains is that a 3m is a0 divided by 3 to the 2m times m factorial, and what remains is a multiplication of 2/3 by 5/3 by 8/3 up to 3n minus 1/3. Or let's write it as 3n divided by 3 is m minus 1/3. Okay? Now, how do I write a nice expression for what I have here in the square bracket? To do that,
Pi. What the sign of pi?
no, it's not pi. It has nothing to do with pi, as far as I know. You never know if something. I mean, it's a dangerous statement to say that it has nothing.
No, pi to multiply all the.
This is just writing the product of blah blah blah. No, okay, that's nice, but I have a nicer way to do that. Okay, to do that, we have to remind you. I have to remind you of a function that we are going to use many times in
a gamma function.
Gamma function. Thank you very much. So, what do you know about gamma function? Okay, one important feature of the gamma function is that the gamma of z plus 1 is equal to z gamma of z. Do you remember? Have you which course they taught you that?
Mathematics 3.
Map is 3. Okay, very good. So this is. Do you know something else about the gamma function?
Yeah,
What are the gamma of an integer?
it's a n minus 1 factorial.
Yes. Okay. Gamma of m is a minus 1 factorial. Okay. So what is and by and large, gamma is like generalization of factorial. So gamma of half is between 0 factorial and 1 factorial. Right? Gamma of 25.3 is between 25 factorial and 26 factorial. Right? Gamma is somehow filling the gaps between the factorial. Sorry, gamma, yes, something like that. Okay. So, what will be gamma of, let's say, 8/3?
It would be
According to what is written here, it will be 5/3 gamma of 5/3. But what is gamma of 5/3? This is 5/3 times times 2/3 times gamma of 2/3. So you see the trick? If I will start in gamma of m minus 1/3, it will give me m minus 1/3 times m minus 4/3. Right? It will give me all this series. All I have to do is to, at the end, I will end up with a gamma of 2/3, and here is where I want to stop. Right?
Calculate the integral.
So I will stop by dividing it by gamma of 2/3. So this expression written here is exactly that. Okay? And so I can write the A3m. A3m is A0 times gamma of 2/3 divided by 9 to the n, 9 to the m times m factorial times gamma of m minus 1/3. That's the final answer.
Won't it be gamma of m minus 1/3 plus 1? Doesn't it need to be?
Yes, you're right. This will be gamma of m plus 2/3.
Yeah.
And that's why it will. Exactly. Thank you, then. Okay. So now I can celebrate and write down the solution. I have a solution to the 80 function, and my solution is y of x equals to a naught times sum from m equals 0 to infinity of gamma of 2/3 divided by 9 to the power of m factorial, gamma of m plus 2/3, and all this multiplied by x to the power of 3m. Right? This is a solution of the Airy equation. If you plug this, so in that sense I have solved, I calculated explicitly all the terms in the power series. I mean, the fact that the sign have, that I can identify a function like sine from the expansion of sine is not, in principle, not more informative that I can identify the solution of the Airy because I know all the coefficients. Okay? Now, yes.
Why do we specifically have to define the gamma a? Why do we have to specifically define a of 3n for the Airy equation?
Just to practice. There's no. Okay. Now you can ask.
Where it's converge.
Oh, exactly. Thank you very much. Okay, I'm feeling proud. Okay, because apparently the message of the last lecture have percolated down. Does it converge? How do I know? Now, if x is okay, if I have to sum it from m equals 0 to infinity. Now, if x is 32, will this series converge?
Probably not.
I'm going to say yes, just because the form is similar to other functions Taylor series that we know converge.
Ah, okay. Let's be more specific.
Take, for example, e to the x.
E to the x converges for its entire function, right?
Yeah, we like the term, the 9 in the m is basically just, we could say it's like a factor into the x, like e to the alpha x or whatever.
Right,
and so it's just over factorial. And then the extra gamma just makes it decay even faster.
Very good. Okay, thank you very much. So the simplest way to check for convergence is to see whether or not the terms are growing or shrinking as m goes to infinity for fixed x. Right? I'm taking x to be fixed, whatever number you like, and I will check whether or not the terms will go to 0 as m goes to infinity for fixed x. So what is the general term for fixed x? Okay, so the a naught is a factor and gamma of 2/3 is something, is pi over, this is pi over something if you, okay, but what is important is that I have here x over 9 to the power of x cubed over 9 to the power of m. This is this divided by that. You see? Okay? This is something, if x is smaller than 1, if x is smaller than the cubed root of 9, is smaller than square root of 3, then this term by itself is going to 0 as m goes to infinity. You see? If x is smaller than square root of 3, no, not square root of 3, then 9 to the 1/3, right? Right? If x is smaller than 9 to the 1/3, then this is smaller than 1, and as m goes to infinity, this is going to 0, exponentially. Okay? Then, of course, the series will converge. However, what's happened if I'm taking x to be 100? Then clearly I have here a huge factor. and as I take it to increasing power of m, it will explode. However, we have here 1 over m factorial, and you should know that factorial function asymptotically win against any power, right? So x to the n over n factorial is going to 0. Why? Because n factorial for n large is e to the n ln n. So it's going faster than exponential. X to the n when n is e to the n ln x, right? And this is e to the n ln n, so it's going faster than an exponential for fixed x as n goes to infinity. So you know that as n goes to infinity, factorial wins against any power. This does not mean, by the way, that the coefficients are becoming, you see, you have here coefficients and you can plot the coefficients as a function of m. For m equals 0, you have something, 1. It may happen that it will go like that, right? If you start with very large x, it will go like that. But then, eventually, when as m goes to infinity, the factorial is going to win. This was your argument.
Well,
And
no,
now an even better
my
argument.
argument was that we know that e to the x converges. We know e to the x converges, and therefore, and since it decays faster than e to the x,
Yes, okay, and now even better, the situation is even better because, as I told you, the gamma is going more or less when m is large, like m factorial. So in fact, what we have here is not divided by m factorial, but by m factorial squared, which is even better. So as I said, this is a convergent power series, which implies that the function is an entire function. It converges for every x which is smaller than infinity. Period. Good. So this is one. However, as you see, here I have only one arbitrary parameter. And where is the other? We know that there are two independent solutions. Where is the other arbitrary parameter?
we set it to 0.
What?
We assume it's 0 basically.
Yeah, but how do I find this is one function.
No, you just solve it.
You solve with the same
just
thing we
gamma
basically
m
did
plus third.
with a0.
Hmm?
Do
Just gamma m plus third. It's the same. Like it's the same sum, just gamma third and gamma m plus third.
How do you know?
We did it.
No.
No, it can't be, because if it was the same
Where is the
sum,
second-
we wouldn't have
Okay.
separate functions.
I remind you that we have A20, we have A0, and this starts with A3, A6, blah, 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 but we have another branch, this one. A1 is arbitrary, and from A1 we can calculate A4, and from A4 we can calculate A7, and so on, right? So there is another branch, which is A3m plus 1, right? Satisfies A3 times A3m plus 1, is A3m minus 1 plus 1 divided by, okay, now
3m
I have to find out what.
3m times 3m plus 1.
What? Divided by something.
3m times 3m plus 1.
Something like that. In any case, you can, at home, you can calculate the second branch, which starts at x to a1, and you will find out that this is plus a1 times the sum from m equals 0 to infinity. Now you have gamma of 4/3 divided by 9 to the m times m factorial times gamma of m plus 4/3 times x to the 3m plus 1. Right? So these are the two linearly independent solutions of the Airy function with two arbitrary coefficients that are a1 and a0. I have only one comment here, which is to say that, where the hell I wrote it? Yes. That in the books, the two solutions of the Airy functions, I told you are called Airy and Bailey, right? And Airy of x is this y with a0 equals to 3 to the minus 1/3. If a0 is 3 to the minus 1/3 divided by gamma of 2/3, and a1 is 3 to the minus 4/3 divided by gamma of 4/3. Does that make sense? Yeah, no, this is true, of course. And the Bailey function is this with a0 is 3 to the 1/6 divided by gamma of 4/3, and so this is divided by gamma of 4/3, and a1 is 3 to the minus 5/6 divided by gamma of 4/3, and this is with a minus. I hope that I copied it correctly. I think so. So 3 to the minus 2/3, 3 to the minus 4/3 with a minus, 3 to the minus 1/6, and 3 to the minus 5/6. Yes. So these are the Airy and Bailey functions. I mean, just a definition of a0 and a1, nothing else. What's nice in this particular choice of a0 and a1 is that the Airy and the Bailey have a very definite behavior. So if this is x and this is 0, the Airy function is the Airy function. Both of them are oscillating here. The Airy is oscillating here. It goes to here somehow, and then from here it goes to 0. And the Bailey is oscillating with a phase with respect to the Airy here, and then it goes to infinity. So at least when you have boundary conditions at infinity, you want your, if you want to solve the Schrödinger equation, then you take the Airy and not the Bailey, right? It's like the growing and decaying exponential. You want to take the, but this is only in the positive x region. In the negative x region, they are oscillating, and I have to put the threat already on the table that we are going to use Airy and Bailey a lot during this semester. Right. Okay. So what I have shown now, it was only an example, but an important example, but an example. And this example shows how to write the solutions of a differential equations using power series and how to check that the answer actually converges, right? And you see that suppose we didn't have this n factorial in the denominator. What will happen then? Right?
What is the question?
Can you tell me what will happen if we will not have these two terms in the denominator?
It will diverge.
It will diverge for every x,
No
Nine,
term.
third root.
right? Then when x will go to infinity, we will have x to the power of 3m divided by 9 to the power of m. So I will say that if x is smaller than 9 to the power of 1/3, it converges, and if it's higher, it diverges, right? So in some cases, we have infinite radius of convergence, which is the Ailey function is an example. In other cases, we have a finite radius of convergence, depending on what kind of series we find out in our calculations. Do you understand that? So if you understand that, or at least you kept silent because you don't want to say anything, but I will assume that you understand that. Then we can say something about the general theory of partial differential equations. Now, I will regard in this, in what I will say, only second order differential equation, but you ought to know that there is a very simple generalization of this to any order differential equation. Physicists usually ended up with either first order or second order differential equation, right? First order is usually exact and we know how to solve. Second order is difficult. Third order we almost never have. So let's speak about third order, but the generalization to higher orders or to lower orders is trivial. Everything I'm saying is completely generic. It's not for second order. The second order is just an example. Okay? Are you with me? So the most generic second order differential equation has a form y double prime plus a of x y prime plus b of x y equals 0. I'm thinking about homogeneous equations. But actually it's okay. The inhomogeneity we will consider later on, but it's not a big problem. Okay? So why I'm not writing like c of x y double prime? Because I can divide by c of x, right? So the most generic second order differential equation after some sort of normalization, if you want, or calibration, such that the highest derivative will have no coefficient, I will end up with such an equation. Now, there are exactly three possibilities. Okay? What I want to do, I want to take a point x naught and to write the solution y of x in a power series sum from n equals 0 to infinity of a n x minus x naught to the power of n. Right? But I did in the Ailey example, I expanded when x naught was 0. But this is not necessary. I can write an expansion around x naught equal 5. It's headache, but it's doable, and so on and so forth. Right? And of course, I can write an expansion again around x naught equals I. Right? It shouldn't be real. It can be an imaginary. X naught may be an imaginary number. Okay? So, case number one. Case number one, I told you there are three cases. So case number one is a case where a of x naught and b So both A and B and B of x are analytic at x naught. You see? For example, in the area equation, what was A?
This is 0.
0. What was B?
And
Minus x.
Minus x.
And both A and B are analytic at 0. You see? Very simple. Okay? In that case, when both A and B are analytic and at x naught, so now suppose we have, this is a complex plane now. This is real x, and this is image x. And we have chosen x naught to be generic point in the complex plane. This is x naught. Okay? If both A and B are analytic at x naught, have no singularity, behave, no branch cut, behave nicely, then this program, expanding it this way, will work. We have a theorem by Mr. Oops. That's how we spell his name. C-H-F. Yes. Mr. Fuchs proof that we can expand the y exactly this way, and the series will converge, but not at any point. We have to find, so suppose I would like to expand it around this point. You have to find the closest singular point of either A and B. So suppose A, for example, A of x is singular here. Okay? If this is the closest singular point, draw a circle, right? This is the radius, supposed to be the same radius. No, I didn't. Right? Draw a circle like that. Still not a nice circle, but you see, around the with a radius that is exactly the distance between this and the closest singular point, and this series, Mr. Fuchs guaranteed, he signed, in the bank, that gave us a guarantee that the series will converge within this circle. Note, this does not mean that the series diverges outside this circle. It may converge, but this is not guaranteed by Mr. Fuchs. Okay? We have no guarantee that it will converge here or here, right? But within this circle, this disk, we have convergence. We will have two solutions that converge and everything is nice. Okay? This is the first part of the general theory of solutions of partial differential differential equations. And of course, you may think about third order equations. Then you have function A, function B, and function C. So all of them should be analytic and blah blah blah. Okay? Any questions about that? Next. And this is called regular point. Ordinary point. Ordinary. So x0 is an ordinary point if both A and B are analytic at this point, and in that case, we know that this program of writing a power series will work, and we are going to calculate everything. The next possibility is a case where one of them, at least one of them, A or B, is not analytic, but x minus x naught times A of x and x minus x naught squared times B of x are analytic. Okay, you see? So, if, for example, A of x is going like 1 over square root of x, A of x is not analytic at 0. Okay? But x times A of x will be analytic. Okay? And if B of x is 1 over x, then again, B of x is not analytic, but x squared times B of x is analytic. The intuition, just as a general intuition, to understand what this condition means, you may think about dimensionality. So think about x0 is 0 as our x0 is x equals 0, right? Now, this term dimensionally is going like 1 over x squared, you see? This term is going like 1 over x, and if x diverges like 1 over x, this term will diverge like 1 over x squared. So it will compete with the strongest singularity, unless we will multiply it by something that will remove the, right? So this implies that although A of x is singular, this term is still negligible with respect to this term when x goes to 0. Right? And the same thing here. But this is just kind of intuition. This is and such a point is called, have the absurdic name, regular singular point. Right? The point is a regular singular point if it satisfies that. And what can we say about so the theory of ordinary points is due to Fuchs. The theory of regular singular points is due to Mr. Provinius. And Provinius showed that at least one of the solutions have the form y equals to x to the alpha times the sum from n equals 0 to infinity of an x minus x0 to the alpha, and this is xn x minus x0 to the power of n, right? So the point is you have the same thing, but n is not integer anymore, right? Because you have this alpha. So if alpha is 1/2, for example, then you have square root of x and x to the 3/2 and so on and so forth. This is one solution. The other solution, this is one solution. Now, if you have, we should have two solutions. So the other solution is either also in this form. If you were taught that in one of the courses, and there is a index equation here, if you remember, whatever. The other solution is if life are good, have the same form with different alpha, right? And if life are bad, then it will be something like x minus x naught to the alpha times ln of x minus x naught times sum from n equals 0 to infinity of an x minus x naught to the power. Yes.
So it has two solutions. One of them takes these forms, Or
one of them for sure will take this form. The other one is either taking this form or is a little bit uglier and have this logarithmic thing. Okay, and of course this is true for second order. If you have third order, then you may have one like that, and one like with log squared, and so on and so forth. I asked the instructor to try to remind you the properties of such things. And now we have the third possibility. What is the third possibility? So first possibility, A and B are analytic. Second possibility, one of them at least is not analytic, but these two combinations are analytic. In the first case, it was an ordinary point. In the second case, it was a regular singular point. And now there is a third case in which, x0 is not an ordinary point and not a regular singular point. In which case, we are going to refer to such a point as irregular singular. Right? These are the three options. Ordinary point, regular singular point, and irregular singular point. And the definition of irregular singular point is that it is not an ordinary point and not a regular singular point. Okay? Okay, let's do some training. So, the simplest example, by the way, what can you say about the area equation?
It is asymptotic.
It is what?
Asymptotic.
Asymptotic. What does it mean?
I can get a form.
To say something is asymptotic is like to say something is equal to. It's a meaningless statement. If you are saying something is asymptotic, you have to add two pieces of information. Something is asymptotic to something else, you have to add the something else, as x goes to x naught. So you should give me three pieces of information. Function, another function, and x naught. Otherwise, it's a meaningless statement. So, for example, what I have showed you here, and actually you can see it from this general definition, is that the area function is and have x that x equals 0, x not equals 0, is an ordinary point of area equation. You see?
Every x.
Hmm?
Every x is ordinary point.
Sorry?
Every x is ordinary point.
Okay, now you are saying every x is ordinary point.
Yeah.
Yes and no. Why? Because there is one important point,
Infinite.
infinity. Right? So, what about x naught equals infinity? Is that an ordinary point of the area equation? How do I examine such a weird question? Okay,
See if it is converged.
but I can't put x equals infinity. Right? To put x equals to 0, I know. To put x equals to infinity, I don't know. So here is the trick.
if you want to examine the analytic properties of something as n goes to infinity, what you ought to do is to define t equals 1 over x. So A, which means that x is 1 over t, right? So when x goes to infinity, t is going to 0. So all we have to do is to make a change of variables and to write the area equation in terms of t instead of in terms of x. You see? So for example, if I'm asking what is dy dx, if I have dy dx by the chain rule is dy dt dx. And what is dt dx?
Minus 1 over x.
This is 1 minus 1 over x squared dy dt, or minus t squared dy dt. You see? So every derivative will be replaced by z. Every derivative with respect to x will be replaced, so d dx will be replaced by minus t squared d dt. Now, what about d2 while to dx squared? To dx squared, yes. What is that? So I should take this. This will be minus t squared d dt acting on minus t squared d dt acting on y. And what will be the result? Right, so d2 dx squared will become t to the fourth d2 dt squared. This is when the case when I'm taking this d dt and acting on that. Plus 2t to the 3 times d dt. This is when I'm taking this and acting on that. So if I would like to write the area function, the area equation in this language will be t to the 4 times y double prime, where now double prime is prime with respect to t. Right? The second derivative of the term, or maybe I will write it as y d dot. Now, yes? Dot is derivative with respect to t. Plus 2t cubed y dot equals to what? What I have on the other side?
1 over t.
Y over t, because x is 1 over t. This is the area equation after the change of variables. Okay? Now, you tell me, what kind of... now, the point t equals 0. You see, t equals 0 is x equals to infinity. What can you tell me about the analytic properties of the solution as t goes to 0?
Irregular. Irregular.
How do you see that?
You need to divide by t to the 4.
Okay, we can write it as y d dot, we divide by t to the 4, plus 2 y dot divided by t, minus y divided by t to the 5 is equal to 0. Right? This is area equation for t, where t equals 0 is like x goes to infinity. And what we find out is that this, you are saying it's an irregular singular point. Because of which term?
Both. The t to the 5.
Exactly, because this term by itself, so we are saying a is going like 1 over x, but you multiply it by x and it removes the singularity, but this term is going to keep. So this is, area equation has an irregular singular point around at infinity. Right? Infinity is an irregular singular point of area equation. Very good. Now, so let's try to get some feeling about what horrors we expect to happen when we have an irregular singular point. Okay? To do that, I will use solvable equations, which are first order. So I just want to demonstrate what kind of horrors we should expect when we try to expand something around irregular singular points. So let's speak first about the first order equation. Y prime is equal to 1/2 y. So y prime, say, minus 1/2 y is 0. What can you say about the analytic properties of this equation as x goes to 0? So all you have to do is just to forget about, you have only a of x. You have only a of x, right? So what is a of x? Or b of x. You have only b of x. What is b of x? What? 1/2. 1/2 is analytic everywhere. So this function is analytic everywhere. And you know that the solution is y equals to e to the x over 2. Yes? You agree with me? Times a. And this is an entire function. So this is an example of an ordinary point in a first order equation, so we can solve everything. It's exact equations. But you see that the solution of an ordinary point is behave quite nicely at, say, x equals 0, at the ordinary point. Okay? Now, next, y prime is 1/2x times y. What's happened now? What kind of point is that?
Regular singular.
This is a regular singular point. Why? The highest derivative here is 1. So this is going like, dimensionally speaking, like 1/x, and this is going like 1/x. Right? If you multiply this by x, it will be analytic. Okay? Now, what is the solution now? Again, it's an exact equation. We can write it as dy over y equals to 1/2 dx over x. And integrate both sides. What I will get?
It's square root.
So ln y is 1/2 ln x. And now I can exponentiate both sides and get what?
Y equals root x.
Equals what?
X squared. No, square root of x.
Thank you very much. Some constant, okay, here I have a constant, right? Some constant times the square root of x. Okay? So this is a regular singular point. You see that what we get is some power, but the power is fractional. We have a fractional power, and at 0, what we have? If we have square root, what kind of property square root of x have at 0? Analytic property.
It's defined, but it's
When you want to define square root of x on the complex plane, what's the main problem?
there's multiple values.
Exactly. You remember that if you write x as r e to the I theta, right? So square root of x is square root of r, which is nice, but e to the I theta over 2. And then, when you take theta complete cycle, you have two different values. In order to avoid that, you should introduce branch cut, right? So square root of x have a branch cut at 0. This is the kind of troubles that you have when you have a regular singular point. And now let's think about y prime equals 1 over 2x squared y. This is a irregular singular point because dimensionally speaking, this is going like 1 over x, this is going like 1 over x squared. So the dominant thing as x goes to 0 is not the highest derivative. And now I can write again dy dx is now 1 over 2x squared. Sorry, dy over y is 1 over 2x squared dx over 2x squared, right? And if now I am, what will be the, so what will be ln y?
Minus 1 over x.
Minus 1 over 2x.
No, 1 over x.
1 over x minus.
Wait, no, it's 1 over 4x. Wait, no, 2x, yeah.
2x. Okay? X to the minus 1 minus x to the minus 2. Right? Yeah. Which means that y will be a times e to the minus 1 over 2x when I exponentiate that. Okay? Now you see, this was a nice, well-behaved function as x goes to 0 with its entire function. It has a Taylor expansion, everything. This one is not so nice because as x goes to 0, it must have a branch curve. So it's kind of non-analytic, but it is still like only multiplied by a power, right? It's a power. This function, as x goes to 0, starts eating babies, right? It's something that horrible thing because as x goes to 0, this goes to actually 0, but in a non-analytic manner. You cannot, this is an essential singularity. You cannot expand it in powers of x. Not in powers of x and not in fractional powers of x.
Also, it's a really annoying singularity because on one side it just approaches 0, and the other side it approaches 0.
Yeah, it's x equals 0 of this is an essential, this function has an essential singularity. So this is the general properties of although, you know, it's not proof and it's just an example and it's with the first order equations that we can solve, that are exact and we can solve analytically, still you can see you can get the feeling of what are the properties of in these three cases. Okay? Good. Do I want to give more examples? Okay. I was way too slow this time. Okay. So we will start now the main part of the course is starting now, right? Although I have only 10 minutes, but I will continue now. So what we want to do is to know how to extract some information from for the behavior of a function around an irregular singular point. So what I did this time is I showed you the Airy function, with the expansion of Airy function around 0, which was expansion around an ordinary point. And now I would like to return to the Airy function, but now I want to analyze the asymptotic behavior of Airy function around x goes to infinity, which, as I showed you before, is an irregular singular point, and the function must do horrible things around x goes to infinity. Okay? And we know that we have absolutely no chance to proceed by expanding it in a power series, because it's not a power series. It's something like e to the 1 over x or something like that, right? We do not expect it to be a nicely behaved power series. Okay, so what should we do? There is only one way to proceed, which is to okay, I will do, first of all, this is just a technical trick, but important. Let's write y equals to e to the s of x. Y of x is e to the s of x. This is for free, right? Okay? And how the equation will look like?
S prime times e to the
S. What is y prime?
Y prime is s prime times
S prime into the s. What is y double prime?
s prime squared
S prime squared
plus s
plus
prime
s double prime times e to the s. Okay? Therefore, I can write this equation as s double prime plus s prime squared equal x, where the e to the s cancels from both sides. Do you see that? Very good. So I have taken a linear and homogeneous differential equation, right? And I replaced it by what? By nonlinear, because of the square, and inhomogeneous differential equation. It's like trading, I mean, מחליף פרה בחמור גדול. Right? We worsen our situation. Okay, but this is what you do. So, first of all, I would like to emphasize that to solve this equation and to solve this equation is exactly the same thing, right? If I know what is s of x, then I know what is y. I just have to plug it in. So, by no means such a trick can help you in solving the equations exactly, right? This is just there is a law of conservation of hardness of problems, right? You cannot take hard problem and make it easy problem by just substitution, idiotic substitution, right? If it's easy in whatever coordinate system you have. If it's hard in whatever coordinate system you have. So this is just this is a meaningless manipulation. The real thing, the real important thing is that now I would like to erase this equal sign and replace it by a asymptotic 2 sign at x goes to infinity. Right? So now it's a completely different story. Now I have a completely different story. This implies that this is asymptotic to that as x goes to infinity. In the meaning of the meaning of asymptotic 2 is what we have defined last lecture. Okay. Now you remember what I did last time when I had 3 terms in an equation and I would like to analyze it asymptotically.
Divide by multiple terms.
No. What I did was dominant balance. So I assume now that if the devil did not took care especially on this equation, as x goes to infinity, one of these terms will not be important. Right? Okay, so either as x goes to infinity, s double prime is asymptotic to x, or s double prime is asymptotic to minus s prime squared, or s prime squared is asymptotic to x. Okay? These are the three options. Let's check them. What we are checking for? Consistency. Right? Here we have neglected that we assume that s prime squared is negligible. Is that true? Right? Here we assume that x is negligible, and here we assume that s double prime is negligible. Right? And the question is, are these assumptions consistent? Okay, that's it. If s double prime is asymptotic to x as x goes to infinity, what is implied about s prime?
That it's asymptotic to x squared.
So it should be asymptotic to x squared over 2. Other than x squared, who cares about the 2? Right? Which means that s prime squared is what? How x prime squared will behave? Like x to the 4. And clearly, as x goes to infinity, x to the 4 is much larger than x. You see? So this option is inconsistent. Next. Here I assume that s double prime is asymptotic to minus, forget about the minus, I don't care. I'm speaking now about size, not about signs. So s double prime is going like s prime squared. This implies that s double prime is going like s prime squared. What do I want to do?
What's wrong?
So I will define, let's say, q as s prime. Okay? So what is written here is q prime is asymptotic to q squared. Right? Which implies that dq over q squared is dx. Right? So 1 over q is going like x, so q is going like 1 over x, so q is s prime. So s prime squared, which is q squared, is going like 1 over x squared. As x goes to infinity, s prime squared, which is q squared, is going like 1 over x squared. Is that consistent with neglecting x when x goes to infinity? No. Because clearly x is much larger than 1 over x squared as x goes to infinity. So this also goes away. This is an inconsistent. And now we know that this must work, no other way, right? So we know that s prime as x going to infinity is proportional to square root of x, right? Which implies that s double prime is what? Is going like 1 over 2 square root of x. And this is consistent because now s prime squared and x are going like x as x goes to infinity. And s double prime is going like 1 over 2 square root of x, so it's going to 0. So this is the correct answer. And the correct answer implies that what? That s, what is s now? If s double prime, if s prime is going like square root of x, what is s?
X to the power of 3/2.
X to the power of 3/2 times 2/3. You see? So this is the asymptotic behavior of s as x goes to infinity. Now what about y? What?
You put it on the X.
Y is e to the s. So apparently we would like to write y is asymptotic to e to the 2/3. By the way, this is plus minus, and here we have plus minus, right? Because we took the square root. So plus minus 2 squared x to the 3/2, which is the correct behavior of the area function as x goes to infinity. I remind you that when I plotted the area functions, I told you that there is a Bailey that diverges, and there is an area that goes like that as x goes to infinity. And if you check, you will find that this diverges like e to the 2/3 x to the 3/2, and this goes to 0 like e to the minus 2/3 x to the 3/2. Okay? So see how easy it was for us to write down the behavior of the area function as x goes to infinity. However, there is some, this is true. What we did here is in the jargon, in the technical jargon, it's called, we have calculated the controlling factor. However, although S is asymptotic to Z, this is true, according to our calculation, this is wrong. Can you understand why?
It's not consistent.
No. It is true that this is actual behavior of the area function, but using this sign should be done with care, right? What I told you is that f is asymptotic to g at x0 if the limit of x goes to x0 of f over g is going to 1. Now, can I say that e to the f is asymptotic to e to the g?
No, because it's f minus g.
Exactly, because then it requires me to say that the limit of e to the f minus g as x goes to x0 is going to 1. And this is not guaranteed. Right? So we have to understand what to do here. This is correct in terms of reflecting the behavior of the area function as x goes to infinity, but the usage of this sign requires more delicate treatment that we are going to do next time. Thank you very much.
I have one question.
Yes.
When do you know to cut them?
Huh?
How do you know when to cut the sums? Like there's infinite sum, and
Yes.
the last variable, any sum, like you don't have a connection to the next. Like we did it with the area.
Mm-hmm.
So if I cut it in n equal 5,
Yes.
so a15 there is no, like you don't have a pair because the other sum
I didn't understand.
I need to cut, like if I want to calculate it numerically,
Yes.
I need to cut it somewhere.
Of course.
How do you know where I cut it?
The simplest way to know that is to try to get I mean, you have, as I showed you, you have something like x to the 3 divided by, and here you have n factorial squared, right, up to factors, and here you have x over 9, 3, right? So you can say that this is going like e to the 3 ln x, say forget about the 9 for example, right? And here you have n factorial squared is going like e to the minus n ln n times 2. Right? So, wait, I should have an n here. Sorry, this is x cubed to the power of n. So I have n ln x, right? Something like that. So you look at the function n ln x minus 2 ln n, which is that, and you start seeing when it stops growing and start decreasing. This is, I mean, you took 10 times the point when when it starts decreasing, and this should be a good estimation for where to cut the summation.
והשאלה השנייה שלי,
כן.
מה שאני לא הבנתי, זה אם אתה רוצה נניח ב-M15,
כן.
אז כאילו A45 נמצא רק בצד של החזקה אחת, רק בחזקה אחת, כאילו בחזקה השנייה הוא לא נמצא, כי הוא לא קיים.
לא הבנתי.
כי אתה עושה סכום אינסופי, נכון?
נכון.
עצרת
אותו ב-10.
עצרת אותו ב-10.
כן.
אז הסכום נעצר בנגזרת קודם, כאילו אין לך את ה-A ששווה לו, הוא לא קיים, כי עצרת אותו כבר.
So last time last lesson we recap all of the material about how to solve ordinary differential equations. Today we will learn fascinating material about ordinary points, regular singular points, and we will say something about irregular singular points, but in the details we will discuss them in the next few tutorials. So in physics we usually encounter this type of differential equation. And there are some points that can change this equation. For example, let's call this point x0, and these two functions, p of x and q of x, may behave differently in the vicinity of this point x0. And in order to understand behavior of these functions, usually we just look at the point, plug this point into a function, and decide whether it's a good point for function or bad. So by good point I mean that in the vicinity of this point both p and q are analytic, so they have Taylor expansion, and if them don't have Taylor expansion, we call them this point singular point. So first type of points called ordinary points. Or OP. In these points, both P of x and Q of x analytic. Or in other words, they can be seen as some Taylor series. Okay. Then, if in this x0 these two functions diverge, we call this point singular point. So second type of point is singular. So on this point, P of x and Q of x are diverge. And singular point can be divided also into two groups. The first one is regular singular point, second one is irregular singular point. The difference between those two is following. So, for example, for the x naught equals 0, if x multiplied by p of x and x squared multiplied by q of x, those two functions are analytic, if those two analytic, so we say that x naught is regular singular point. And if one of them or both diverges in this point, so we can say that x naught is irregular singular point. Today, in this tutorial, we will cover only ordinary points and regular singular points. In the next, as I said before, in the next few tutorials, we will also discuss how to solve differential equations with this type of points. Any questions so far? Yeah.
What exactly do you mean by analytic? In what sense?
In a sense that I can write these functions as a Taylor series. Okay, so those functions have all of the derivatives from the first till the end, and analytic means that I can write, for example, p of x as this series. Okay. Okay. Then we have theory. Let's practice a bit about classifying these different types of points. Okay, you have it, right? So the first example will be just harmonic oscillator. And the question is whether this equation has ordinary points, regular singular points, or irregular singular points. What do you say?
It's ordinary. Ordinary.
Yeah, I mean every point, every x, right? If we plug any x into equation, we see that nothing really changed. Because if we write this equation in terms of p and q, we will see that p of x is just 0, right? And q of x is constant omega squared. So because those two functions constant and don't depend on x, now it's this equation also analytic and doesn't have any singular points, only ordinary points. Okay. The next one is the Legendre equation. ideas? Yeah.
Regular?
You need to say what exactly. I mean, first of all, you say that, for example, x equals 0 is, and then say whether it's regular singular point or ordinary point.
Okay, so p of x is definitely regular.
What is p of x, by the way?
2x, negative 2x.
No.
Divided by 1.
Look at this equation. So the first coefficient should be 1, right? So that's why we need to divide whole equation by this coefficient, and then it's minus 2x divided by 1 minus x squared. Okay, this is p of x, and q of x just 1 over this. Okay. At what point these two functions
It is
like
singular
problem.
at 1.
Yes.
Minus 1.
Yeah. So in this case, x naught is plus minus 1. We understand that in these 2 points, p of x and q of x are divergers, right? So these 2 points are singular points. Then we know that there are 2 types of singular points. In the second step, we need to figure out whether it's RSP or ISP. What do you say?
It's RC.
Regular singular point.
Why?
Because it's first order polar. You have it's the power of minus 1, not power of minus 2.
No, it's because they're two different singularities. They're not. It's not x0 squared. It's not 1 over x squared in px, and it's not 1 over x cubed in qx.
Mm-hmm. Yeah, right. So in a general way, how we can understand is it regular singular point or not?
Multiplied by x minus.
Yeah. So x minus x naught p of x, right, and x minus x naught squared q of x. So in other case, we multiply this by x. Multiplied by x plus 1 or x minus 1, and plug in this and see that in both cases we will get analytic functions. So it will not diverge if we multiply those two by x plus 1 or x minus 1. Okay, so there's p. There's regular singular point. Good. The next one is well-known Bessel equation. So it's x squared y double prime plus xy prime plus x squared minus mu squared y equals 0. Again, we in the first step divide all the equation by x squared, when we got p of x is 1 over x, right? Q of x is 1 minus mu squared x squared. Again, we have a problem in the 1 point. It's not equals 0. And if we multiply this by x and this by x squared, we will obtain analytic function. So x naught equals 0 is regular singular point. The last one.
Yeah, we don't measure infinity like we did in the class.
Yeah. So we may say something about infinity. What do you think? Is it a regular single point or in this case?
I don't know. It goes to 0 and 1.
Yeah. So if x goes to infinity, this goes to 0, this goes to 1. So 0 and 1 are analytic. You can expand them in different series. In this case, by the way, what do you think? I mean, x equals infinity. What type of singular point it is?
So also 0 and 0.
Yeah?
I think it's a regular. Both are 0 to infinity.
Here it's 0, right?
Yes.
Here is.
Also,
So?
so there's not.
It's ordinary.
Yeah, it's ordinary point. Yeah, and I guess for this equation, infinity is also ordinary point, not regular singular point. Okay. Yeah, and the last one. So p of x 0, q of x 1 over x cubed. And I think it's pretty clear that x naught equals 0 is irregular singular point, because even after multiplication by x squared, q of x still has problem at 0, so it diverges. Okay. Any questions? So far so good?
So we use just for homogeneous equation.
Yeah. Say it again.
So just for homogeneous equations, if the equation is not homogeneous, not equal to 0.
This one?
All of them. So all of equal to 0 always.
Mm-hmm.
If we have equal f should x. Still we do the same.
Well, we need to also understand what will happen to the right hand side. So whether it diverges at x naught or it's analytic. But again, then you solve non-homogeneous differential equation. You, in the first step, solving.
The Vedas?
Yes, yes.
Okay.
So this is just basic stuff what we need to know. And now let's practice with equation itself. So we start with ordinary points. This is the most easiest case. If we have an equation with ordinary points, we can solve it just by Taylor series. We will say that our solution of this equation will look like a Taylor series, and when we need just to plug this into original equation, and our goal is to find these coefficients A0, A1, A2, etc. So for example, let's solve this equation. I know you can solve it without series, right? Just harmonic oscillator with omega.
Probably the worst way to solve it.
Yeah, yeah. What happens if we plug this Taylor series to the equation?
We have to derive it twice.
Yes.
Then get the quotient relation.
So after two derivatives, what we will have? N minus 1 x to the n minus 2, right? This is the first term. And the second term just same, right? When we need to get the recursion relation, how we can get it?
Play with the indexes, like
Okay.
substitute x prime equals no, n prime equals n minus 2.
Yeah, we want to this and this.
Yeah.
They should have the same power.
Yeah.
Right? So and we need just shift index to the two positions, right? So to the A and plus 2 and plus 2 and plus 1 xn, right? So that will be the first series from minus 2, right? To infinity. And this one, just leave it as it is. So we do all of the calculations, then we got the relation between n plus 2 and an, and finally we will get that this is y is just the sum of sines and cosines. Yeah. Okay. Because this is too easy for us for our course, we just skip the other examples of ordinary points and start discussion about regular single points. For these points, there is one bulletproof method. I think some of you are familiar with this method, right? Frobenius. Yeah. Then we say that our solution to this equation will look like x minus x naught n plus r. So in the x naught, it's a regular sum. Okay. The math is the same. Just take this series, plug in to the equation. When we will obtain these two numbers for r, and there are three cases when r1 is not equal r2, and their difference is not like a natural number. The second case, then those two are equal, and the third one, this one. So they are not the same, but the difference is a kind of a natural number. Okay. So for the first example, we will see. Look at the Bessel equation. So by the way, a useful example because you can, from this equation, you can cover all of these three cases. Just changing this gives you these three cases. So that's why I decided to pick this equation. Okay. So we know that problematic point or singular point is x equals 0, right? So that's why we use, we say all of this stuff that this is regular singular point, and that's why we need to solve this equation with Frobenius series. So, and the solution will look like this. Okay. And let's just plug this to the equation. Okay. Second derivative from the first one, we will get n plus r. From the second, n plus r minus 1, right? And then we have x is x squared, x in the power n plus r minus 2. After multiplying this by this, we just will get this one. Okay. same logic. N plus R x n plus R. Again, should be -1 here, but because of this x, we will get completely the same powers. Then plus, okay, let's here open the brackets. So a n x n plus R plus 2 because of x squared minus new square a n x n plus. Okay. So the next step is group terms with the same power effects. Okay. So n x n plus R, and in the brackets we will have n plus R, n plus R minus 1 plus n plus R, and here minus u squared. Okay. And this one I put it to the right hand side, so minus a n x to the power n plus R plus 2. Okay. This is our equation. Just plug in the solution and obtain this. By the way, we can make it this expression even simpler, right? Let's rewrite it. So
Taking out.
yeah.
So
I take out this one, right? And this term is just 1, right? Just 1. Here is -1. So after simplification, we will get n plus R squared. Okay? And again, we want to get obtain the relation between the current relation between those two coefficients. But the problem is that here is x in this power, here is x in this power. So we just need to shift index of summation. Switch board. So let's write it in this way. first power of x here is r plus 2, right? The first power of x here is r. Okay? So that's why let's just write the first two terms of this. Okay? The first term is a naught x to the r squared minus squared. Okay? This is the first term. The second will be a1 x r plus 1 r plus 1 squared minus mu squared. Okay? Here is the rest of the summation. Then we say that a naught is not 0. Then, okay, let's write this equation in this way. I'm returning this term to the left-hand side. Here will be plus. Because all of these should be equals to 0, right? Each term should be 0. Okay. Let's say that a naught is not 0, x to the r also not 0, then this should be 0. Right? Then we get r1, r2 plus minus two roots. Okay. Then we look at this term, and because we already know the values of r, we can easily see that plugging these values to this expression will not give us 0. Right? The only way how this thing can be 0 is this. Okay? So we know that a naught is not 0, a1 is 0, and then we need to do something with those sums. Okay? Series. Let's shift this to shift this summation from 0. So n just it's n minus 2. Okay. In this case, sum will start from 0 to infinity. Here is n minus 2 x n plus 2. No, plus 2. Yeah. Plus 2 and plus r plus 2. Here is n plus 2 plus r squared minus mu squared plus this series. because now power of this x and this x the same, we can combine these two terms. So x n plus r plus 2. Here is a n plus 2 multiplied by this term, n plus r plus 2 squared minus mu squared plus a n. Now we know that these two terms are 0, and then if we want to do that the rest of our expression will be 0, what we need to know? This bracket equals 0. So, and that's how we will get the recurrence relation. There it is. Okay. Now, then we get the recurrence relation. We can basically find the solution. Remember that solution is this y function, and our goal is to find these coefficients of expansion, right? Okay. So for the let's do it for the Bessel function. Can I erase this? Yeah. So let's start with n equals 0. Okay. Then a2 is minus a naught, and here we have r plus 2 squared minus mu. Okay, it's our first factor. Then, for n equals 1, we have n3 is minus a1, and here we have also. But remember that here we wrote that a1 has to be 0. Okay, so that means that doesn't matter what I have here, right? It's 0. And we can apply the same logic and say that because of a5 is a3 divided by something, a3 is 0, so, and the same for a7, a9, a11, and so on. So if index is odd, the coefficient 0. Okay. But let's calculate even coefficients. So A4 is minus A2 divided by R plus 4 squared minus nu squared, and then we can plug in A2, A0 about minus, then R plus 4 squared minus nu squared multiply by this R plus 2 squared minus nu squared. Okay. And then we just continue to do it, and we will get that the general expression for a, let's call it 2k, or in our it's 2n, so even coefficient, will be minus 1 to the power of n, then A0 for n factorial n plus 1 plus nu, 2 plus nu, and so on and so forth till n plus.
In the lecture, we learned to simplify that into the gamma function.
Yeah, so that's fine. I just wanted to say that probably in Adapt show you how you can rewrite this coefficient using two gamma functions. Okay. Yeah. And that's how we can get our solution. So we know coefficients and the solution just this. Okay. And from that moment, the magic happened. When we found these two values of R, we need to look at them and decide with what case we deal with. As I told you, the first case is then R1 minus R2. It just is not integer. Okay. It's the simplest case. For example, if in our basic equation nu is 1/3, then we have R1 is 1/3, R2 is minus 1/3. As you can see, the difference is not integral. So in this case, you are doing the same thing that as we did right now for each value of r. So, and that's basically you will get y1 of x as some series with coefficients x n plus 1/3. That's the first solution. And the second solution is simply the same, but with, of course, different expansion coefficients and different power. But logic is the same. It's the most simplest case. The second case is then you have repeated root. By the way, in the Basel equation, it's the only one value of mu that can provide us with the second case.
Well, now it becomes.
Say it again?
Nothing.
I mean, you have only one number that is the same with plus and minus.
Yeah.
So that's why for this equation, it's the only one. But of course, you have a lot of equations with this case. So it's not necessarily should be Basel equation. So in this case, what we do is we find the first solution as usual as a power series. Do the same, plug in the equation, then obtain this general formula for the expansion coefficients, and then plug it here, and that's how you obtain the first solution. The second solution will look like y1 of x ln x plus same series, but of course with different expansion conditions. So because we use a Frobenius method for sort of a, because this Basel equation, you can see it as kind of a general form of earlier equation, right? If this term will be just one, we know that this is just earlier equation, right? And what we usually do when in the earlier equation we have this repeated root. We discussed it last time.
We multiply
by ln x. Ln x. Okay. So that's why you sort of have here this ln term. Okay, for the repeat root. again, you know y1, you don't know this coefficients, you plug this monster to the original equation, calculate, and then after a couple hours you will obtain this equations. But in the Bender's book you can find the easier way how you can find these coefficients. So please, if you're interested in the fast solutions and don't want to waste your time plugging in this to this, look at the Bender's book, and you'll see there sort of a shortcut for the second solution. Okay. Okay. And the last one, last case, the most horrible one, is then
It is 1/2.
for 1/2. Yeah, or 4 or 42. Yes. So then R1 minus R2 is integer. Okay. If it's integer. In this case, for the first solution, nothing special. We need to take the largest value of R. Let's say R1 bigger than R2. So for the first solution, y1 of x, I plug in this series to the original equation and doing the same procedure to get the coefficient. Then for let's discuss the second solution. So let me go back to this recursion relation. Let's rewrite it in this way. an plus 2 multiplied by n plus r plus 2 squared minus mu squared equals minus an. Okay. And for example, nu will be 1. Okay. So we want to write it for the second root. Okay. An plus 2. Here is let's use the formula difference of squares. N plus r plus 2 minus mu. Here's n plus r plus 2 plus 2. Okay, let's now plug mu equal 1 to the equation. N plus 2 n plus r plus 1, first one, and n plus r plus 3. And we know that r is plus minus 1 because we used already the biggest r for the first solution, right? Here we dealing with r minus 1. Okay. So plus 2, just n. Here is n plus 2. Okay. So we got this recurrence relation. Does someone see problem here in this relation?
At n is equal to 0.
Okay. What's the
Divided
problem?
by 0.
No, I mean you don't need to divide it, this equation by this. Just look at the right hand side and left hand side. What do you see?
Minus and the plus.
Okay, let's for the first term n equals 0. Okay. So we have a2
A0 is 0.
multiplied by 0 equals minus a0. Do you remember that we said that a naught can be 0, right? So right hand side non-zero, left hand side 0. Something strange, right? And if that happened, if you got 0 from one side and non-zero for another side, I call it fatal case. This means that you, for the second solution, Frobenius series doesn't exist because you see contradiction here, right? So we cannot use a Frobenius solution. That's why the second solution will be not in this form, but will contain also logarithmic term. And this logarithmic term help us to avoid such a situation. Okay. So this is the second solution in a fatal case. But for example, as you suggested, nu equals 1/2. The difference also integer 1, right? And let's look at this case. If 1/2, R1 is 1/2, R2 is -1/2, and the difference is 1. So it's integer. Then we're in the third case. So the biggest R goes to the first solution as a Frobenius series. Okay, and let's look at this equation in for the second solution. Okay, so this is it's not general, but we need to change this and this to one, not this. Yeah.
Is on the top.
Here. Right. Okay. Thanks. So an plus 2. So n plus minus 1/2. Yeah. Minus
n plus 1. A lot of minus 1 minus. Yeah, plus 2.
Yeah, just plus 1. Thanks. And here, just n plus 2. Beautiful. No, we have no problems with that. Just regular recurrence relation. And if you don't have any problems with that, the second solution, as usual, will be in the Frobenius form of the Frobenius series. So no problem. Okay, and that's why the second solution just plus. Okay. This is it about regular singular points. Do you have any questions so far? Yeah, a couple words about irregular singular points, and we will finish. So I just want to show you why the Frobenius method fails when we encounter with irregular singular points. So let's write the solution in this form, usual Frobenius, and let's plug it to the equation. Okay, let's write this first term of this series. So it will be a naught r plus minus 1, and then x to the r plus 1, yeah, plus the series from 0 plus 1
N plus 1.
It will be easier to open the second summation.
Yeah, plus 1 thing. Yeah. So again, here we have two roots, right? Yeah. So let's look at the first one. Then again, you see the problem. So, but for the r equals 1, if we plug it here, everything will be fine. So, but because for one root we have a problem, we don't actually can solve this equation by forbidding. We will use different techniques like asymptotic analysis, and WKB, the same from quantum mechanics, and in the next tutorials we can solve this equation. We will show that the solution of this equation behaves like e to the power 1 over square root of x. I think Nadav today told you already how to deal with irregular single points. Okay. We will see it in the details on the next tutorial. So you can find the homework on the MIDA website. The deadline is, I guess, next week. So yeah, tutorial also you can find on the website. What else? think that's it. If you have any question, yeah.
Thank you.
Ah, okay. You're welcome.
Can you explain to me why you can use this method to like calculate y here? What is the problem in this one?
Because, for example, n equals
Yeah.
here is 0, here is non-zero.
Okay.
Because
So
we say that if this, yeah.
it sends every a to 0 because
Yeah.
the
So and you'll get a
zero.
trivial solution, but I mean, why here is y equals 0 is solution, right?
Yeah.
But
Yeah, it sends every a to 0 because a0 is 0.
Yeah.
Okay. Thank you.
The second solution is okay. We can solve with r equal 1, and then just talk about what's both solutions are not good.
both solutions. Yeah.
Okay.
I mean, there is a theory that
If one
that
solution is not
yeah, that this will not work.
Yeah. Can I ask informative question? The homework, can you put it until Saturday, not Friday?
Until
Tomorrow.
Saturday?
Yeah. One, I work for the week. You just
Okay.
and weekend to do to the.
Yeah, okay. I mean, I can move it to Matzah Shabbat.
Thank you.
Okay. You're welcome.
Thanks.
Thank you for uploading the lecture notes this time.
Yeah, you're welcome. I hope it will help you to understand the material.
It did help already.
Oh, good. Thanks. In the tutorial, I think there is a bit more information than I provide in the tutorial, but I mean in the offline tutorial. But it's still useful, so.
Yeah, absolutely.
So bye. See you.
Bye.